The kind of sampling we've been talking about so far is sampling with replacement, which works just fine for situations like tossing a coin, rolling dice, playing gambling games and so on, where you're genuinely repeating the same thing independently over and over again. But when you're sampling people, sampling with replacement is a somewhat unnatural thing to do. You want to write the list of names of people that you've got in your group and then just stick your hand in and pull out a few at random. You're not going to pull somebody out, throw them back in the pile and pull out again. So you're going to want to sample without replacement, and so what we're going to do now is look at adjusting what we know for the case of sampling without replacement, and the good news is the adjustment is tiny. You essentially know what to do already. And so here's some language. I've got a population, and when I say population, most people imagine people, and that's great. You imagine people, and connected with each person, there's the value of some variable you're interested in. So maybe it's that person's age. And so now what you want to imagine is that person holding up a ticket, and on that ticket is the person's age. And you can have the picture of the person in your mind. I, being a statistician, will simply reduce that person to a number, and all I see is the ticket. And so I have n numbers, and that's my population. Well, what did you expect? I'm a statistician. I reduce everything to a number. Right, so I have a list of capital N numbers. At this point, it is a good idea to start imagining n as quite large. Though in what I say, it doesn't have to be large, but for a visual sense of what's going on, it is a good idea to imagine a large population. And the list of ages has an ordinary average of mu and an ordinary SD of sigma. And from this list, I am going to take a simple random sample. I remind you that's a random sample without replacement of little n. This is classic language in the field. Little n, small for the sample size, capital N, big for the population size. And we're going to look at two quantities that you have looked at before. We're going to add up the numbers in the sample and call that the sample sum S. And then we're going to take the average or the mean of the sample and call that M. These two quantities are random variables. The values that you get depend on the sample that you picked out. Which little n of these capital N numbers you got will affect the value of S and equally the value of M. So the sample mean is a random variable. It changes from sample to sample. The population mean is a fixed real number. You might not know it, but it's fixed. So what do we know about the sample sum and the sample mean? Well, it turns out that the expected value of the sample sum is still a number of draws times the average of the box, and the expected value of the sample mean is still the mean of the population, even though the draws are without replacement. Expected values are essentially averages, and averages behave very well under sums. And so there is really no change to what you've been doing thus far when it comes to just looking at the expected values. The formulas are the same as if you had been sampling with replacement. Well, so what's different? These are just estimates, as we said before, and so we need a margin of error on these estimates, so we want to look at the standard errors. And if you think about comparing sampling with replacement and sampling without replacement, so now imagine that you are trying to estimate the average age of your population, and you sample without replacement, say 100 people, and I decide I'm going to sample 100 people, but with replacement. So I'll get an estimate and you'll get an estimate. If you had to guess, which would you say is more accurate? Yours, sampled without replacement? Or mine, sampled with replacement? I think yours, because you have 100 distinct pieces of information. You have 100 distinct people, whereas I have the possibility of getting the same person twice, 3 times, and so on. And so there is an intuition that says that if you do simple random sampling without replacement, that should be more accurate than if you sampled with replacement, because you have n distinct observations in your sample. So what measures accuracy? The standard error. And so here are the standard errors for S and M. More accuracy means smaller error, so smaller standard error. And here we go for the sample sum S. The expected value is a number of draws times the average of the box, as we've done all along. The standard error now is different. You'll recognize this bit. The square root of the number of draws times the SD of the box. That's the same as it was, and now you take that, which is what you would have computed anyway, and you multiply by this factor. What is that? It's the square root of population size minus sample size divided by population size minus 1. Hold that thought for now. Let's look at what happens to the sample mean. Expected value of the sample mean is the population mean. That's what you've been doing all along. The standard error for the sample mean is the box SD divided by the square root of the number of draws. That's what you've been doing all along, but now multiply by this factor, which is a correction for sampling without replacement. And let's take a look at this factor. So first note, it's the same factor in both cases. So the rule for working with simple random samples is do what you would have done for samples with replacement, then multiply the standard errors by this factor. Same factor no matter which standard error you're calculating. How big is the factor? Well, little n is the sample size. What's the smallest it can be? Well, 1, but that's a very boring sample because you have no idea of a measure of spread. 2, yes. And already in that case, this factor is less than 1. So what you have noticed is that when you sample without replacement, the standard errors are the same as they would have been if you were sampling with replacement, except for a multiplicative factor of less than 1. In other words, you're taking your old answers and you're multiplying by a fraction. And so your new standard error is smaller than your old one, which makes mathematically precise this intuitive sense that sampling without replacement is more accurate than sampling with replacement. So what's the moral of the story? The moral of the story is that the formulas for when you're sampling without replacement are the same as before for with replacement. You just multiply the standard errors by what is called the finite population correction, FPC. You'll see that in various places. And that's this factor here, root population size minus sample size divided by population size minus 1. That factor is necessarily less than 1. Once again, it's one of these standard error, standard deviation facts that I'm not going to prove in Stat 2, but at least it gives you the right direction of making the standard errors smaller as you would expect them to be. So let's run through a quick example. I have a population of 1,000 incomes, from which I have a population of 10,000 incomes, from which I am drawing a simple random sample of size 400, so that's 400 drawn at random without replacement from here. I know already that my population mean is $60,000 and my population SD is $40,000. And I am looking at the mean of my sample. What do I expect it to be? Well, I expect it to be $60,000. Give or take what? Well, give or take an SE of the sample mean. How'd you get that? You take the SD of your population and you divide by the square root of the sample size. That's what you've been doing all along. Except now you have a simple random sample, so you multiply by your correction factor, and that is the square root of population size minus sample size, that's your 9,600, divided by population size minus 1, that's 9,999. And that is 2,000, which was your original SE had you been sampling with replacement, times this correction factor, which you should note is awfully close to 1. It's just not such a big deal. It's there, but it reduces your 2,000 to basically 1960. And that's an interesting thing to note, is that the change isn't very great. It's there, certainly. The standard error for sampling without replacement is smaller than the 2,000 that it would have been if you had been sampling with replacement, but it's not that much smaller. So it's a good idea to take a look at how much smaller it could be and in what situations it's smaller and in what situations it really doesn't matter at all. So what I'd like to do is I would like to now start getting into the typical situation in statistics, which is where you have a very large population and you don't have the human resources to go sampling every person in that population, right? You have some question, right, that you're trying to answer. For example, what's the average income in this population? So in principle, you could go to each member of the population and say, excuse me, what's your income? Write that down, then go away and take an average of the capital N numbers. But you don't have the resources to do that, so you take a random sample of these capital N. And that sample size is what we're calling little n, and it is typically considerably smaller than capital N. So relative to the population size, your sample size is fairly small. And so just to fix ideas, imagine that you have a population of 10,000 people and you're taking a sample of size 100. And I want to compare sampling with replacement to sampling without replacement. When you take the first person out, when you draw that first person at random, probabilistically the two schemes are equivalent because you haven't got to person number 2 yet. For person number 2, in the case of sampling with replacement, you throw the first person back and you draw again. For person number 2, in the case of sampling without replacement, you leave them out. So what are you drawing from? You're drawing from 9,999 people. Have you changed the composition very much by taking out one person? Not really. And in fact, if you keep playing this game of drawing one person out and then another person out and then another person, if you take out a small fraction of the population, then whether you're sampling without replacement or with replacement, the probabilities aren't that different. In the case of with replacement sampling, you'll get the same fraction every time, whereas in the case of without replacement sampling, it'll change a little bit, but it changes a tiny amount. And therefore, sampling with and without replacement, even intuitively, becomes pretty much the same in the situation where you're not sampling a lot of the population. Algebraically, what's the difference in the calculation? The only difference is the correction factor. And the correction factor, now let's take a look. Capital N is very large, that's what I'd like you to imagine. And little n is pretty small relative to capital N. So this fraction, while less than 1, is actually pretty close to 1. When you take the square root, it's even closer. And so the factor that you multiply by to correct for sampling without replacement doesn't really have that much of an effect. And so you can simply drop it without a great deal of loss of accuracy. And so when you are calculating standard errors and you're sampling without replacement, then in the typical statistical situation where you have a huge population and relative to that your sample is pretty small, you might as well have been sampling with replacement as far as your calculations are concerned. And so as I said, you already know how to do this. There's nothing new here. And while we're about it, this is just a repeat of what we've just said. You have a very large population, you know its mean in SD, you've got a small, simple random sample, relatively small anyway. And in that case, sampling without replacement is almost the same as sampling with. And now I want you to imagine tens of thousands in your population, and some hundreds, maybe 1,000 or so, in your sample. So then your draws are almost with replacement, and when you have with replacement draws and you are adding up the draws or taking the mean of the draws, isn't the probability distribution roughly normal? Yes, it is, because there's a central limit theorem, and that should be the same here too. And indeed you have a central limit theorem here, sort of, because we're drawing a simple random sample, so we're not exactly drawing independently. They're dependent one draw to another. However, we're assuming sample size large, maybe, 100, a couple of hundred, but small relative to the population. So a few hundreds relative to several thousands, say. In that case, you might as well be drawing with replacement, and in that case, everything that you did before, the normal approximations, valid almost exactly similarly. The distribution of the sample sum is roughly normal with mean, number of draws times the average of the box. SD, square root number of draws times the SD of the box. In the case of sampling with replacement, that was the standard error, and now it's approximately the standard error. Why approximately? What's missing? What's missing is the correction factor, which is awfully close to 1. But the point here is that for a normal approximation, a rough normal approximation, you're doing just fine with your old calculation. And this second statement is the same thing about the mean. The distribution of the sample mean is roughly normal with an average of the population mean and an SE of SD of the box divided by square root of the number of draws as before, regardless of the box that you started with, regardless of the distribution of the population. That's really handy. Because if you have a distribution like, for example, one of ages, and you really don't know what that distribution looks like, you can still say a lot about the sample average because of the central limit theorem. In practical terms, what's the moral for you? In practical terms, the moral for you is just do what you've been doing all along, and you won't be so far off. So we'll take that in a numerical example. I've got a university that has over 30,000 students. Berkeley is one such. And I take a simple random sample of 200 students from this university. I know that the average grade point average at this university is 3.0 and the SD is a half. And I ask, in my sample students, among these 200 students, what's the chance that the average GPA is actually higher? And specifically, what's the chance that it's more than 3.1? Well, how would you have done this before? You would have said, well, okay, there's a box full of GPAs, and the average of the box is 3.0, and the SD of the box is 0.5, and I'm drawing 200 out. So what do I expect that sample average to be? Well, I expect that sample average to be what it was in the box, so I expect 3.0, give or take an SE of the sample average. You play exactly the same game here. The average GPA in the sample is expected to be 3.0 with an SE of what? SE of the sample average, SD of the box divided by square root of the number of draws. What's missing? What's missing is the finite population correction. And that, well, you're taking out 200 out of 30,000. That's going to be almost 1. So you're fine saying you expect it to be, on average, 3.0, give or take 0.03 roughly. And so what do you want? You want the chance that the average is in fact more than 3.1, so you better convert 3.1 to standard units, and then look up your applet, and you've got the chance that in the sample, the average GPA is over 3.1. That's just about 0.25%. So if you step back and look at this calculation, you ask yourself, what did I learn in this section that I didn't already know? Because this is exactly the same calculation that we were doing back in the previous section where the sampling was with replacement. So what happened here? What happened here is you learned that the same calculation works to good approximation when you have sampling without replacement, a relatively small number of students from a large population. And everything is the same except for the approximately in the SE. What's missing is the finite population correction. Why didn't we use that? Well, first, we couldn't. We don't have the population size. It says over 30,000, but I don't know if that's 35,000 or 40,000 or 30,001. So just because I don't have it, I don't have to use it? Well, no, it's not only that I don't have it. I do have some sense of how big it is. It's huge compared to the sample size. And so I know whatever the correction factor is, it's going to be pretty close to 1. So I'm not going to be fussing with that level of difference. And so, instead of getting 0.0353 exactly, I might get, 0.034, I don't know. But I'm just not going to fuss at that level of detail. This, as an approximation, is okay. And so do what you used to do before. Just check that you're sampling a relatively small amount of the population. So 200 is small relative to 30,000, but, as an absolute quantity, it's 200 draws is a lot of draws. So your central limit theorem works fine. Always, the most important special case, zeros and ones, success-failure trials. And now what is the setting? Now you have a population of good and bad elements. So you have good elements that are ones and bad elements that are the zeros. I'm saying you have capital G good elements and B bad elements. Your population size, therefore, is G plus B. And you're drawing a simple random sample of size little n, and you're counting the number of good elements in the sample. We got a number of good elements in a simple random sample. What do you know about that? Some time ago, you knew that it was, hypergeometric. Population size capital N, number of good elements capital G, simple random sample size little n, just as before. So you can write down the probability that x is equal to any number using that hypergeometric formula. Good elements choose however many you want, bad elements choose however many you want, divided by population size, choose sample size. And now we know a bit more. We know that this x is the sum of little n draws at random without replacement from these capital N. And so we know that the expected value of x is the expected value of the sum of the draws. And what did we say that was? Well, that was the number of draws times the average of the box. What's the average of a 0-1 box? It's the proportion of ones in it. And is this a formula that you recognize? Oh, yes, you do. It is the binomial formula NP. The expectation of the binomial, except now the probability of success has a fractional form, number good divided by total number. This is the same thing as NP in this instance. And so what do you have for the standard error? It says, well, compute the SE that you would have computed before. What's the SE of the binomial? Square root of n times p times 1 minus p. The square root of a number of trials, probability good times probability bad. For the binomial with replacement sampling, you'd have stopped there. But you're not stopping there anymore. You're fixing it. You're correcting for sampling without replacement. Simply multiply by the correction factor. So take one more look at the formulas for the expected value and standard error of the number of good elements in a sample without replacement. Same as the formula for the binomial. NP, square root NP 1 minus p, except the standard error is multiplied by the correction factor. The same observation applies if your sample size is relatively small compared to the population size. Then this correction factor is approximately what? It's approximately 1, yes. And so if your sample size is small relative to the population size, then the formulas for the expected values and standard errors are pretty much the same as the binomial. The expected value is indeed the same. The standard error, well, if you just did the binomial calculation, you're going to be pretty close to correct. And once again, for the 100th time, when you have a large population and you're taking out a relatively small number of it, whether you're taking them out with replacement or without, doesn't make that much of a difference. And while we're about it, in this same situation, if your sample size is large but small relative to the population size, then the distribution is roughly normal. So if we have to summarize this, the binomial is the distribution of the number of successes in independent success-failure trials. The hypergeometric is the number of successes in without replacement success-failure trials. So those two are close when you're sampling a relatively small fraction of the population. And if in that situation the sample size is actually in absolute terms large, then the binomial would look like the normal, as you know very well, and therefore the hypergeometric better look like the normal as well. A quick numerical example just to see that the calculations are straightforward. So now I have the classic situation of sampling without replacement, dealing cards from a deck. I have 52 cards, my standard deck, 52 cards. I remind you it has 4 aces. And I'm going to deal a hand of 13 cards. That's a bridge hand. And what I want to know is how many aces do I expect to have in that hand. So the expected number of aces is blank, give or take. What's the standard error on that? Alright, so how do I put this into the situation that we are in this segment? Of course, the number of aces is hypergeometric. Capital N is 52, capital G is 4, and this little n is 13. And I want its expected value here. So the expected value is the sample size times the proportion good. And so let's write that down. We have a simple random sample of 13 elements taken from a population of 52, of which 4 are good. The expected number of successes is the sample size times the proportion good, NP, which is equal to 1. In 13 cards, you expect 1 ace, big surprise. So really, for that, you hardly had to do all of this formalism, but for the standard error it's very helpful. The standard error is now calculated by doing what you would do if you were sampling without, if you were sampling with replacement, the binomial, so square root of number of trials times fraction of ones times fraction of zeros, and then you multiply that by the finite population correction factor, which is in the denominator you have population size minus 1, in the numerator you have population size minus sample size. And so you get, this is the 0.9608 is the standard error you would have got if you were dealing with replacement, and now you fix that by multiplying by this correction factor, which is, noticeably different from 1. It's 87.5% roughly. And so in the end, your standard error for the number of aces is about 0.84. So you expect 1 ace, give or take, about 0.84 in your 13 cards. And so what's the moral of this story? The moral of this story is you're dealing without replacement. For expected values and standard errors, pretend you were dealing with replacement, do the calculation as you would have done, fix the standard error by the finite population correction.